You type a question. ChatGPT answers. It feels like magic, but behind the scenes, there's no magic, only math. Your text gets chopped into tokens. Each token becomes a vector. Those vectors flow through 100 transformer blocks. Out comes a probability distribution over the next token. The model samples from it, repeats. Word by word, the answer appears. In this final episode, we put all the pieces together, from your keyboard to the model's response. AI models don't see words the way we do. They see tokens, pieces of words. The most common tokenization algorithm is Byte Pair Encoding, or BPE. It starts with individual characters and repeatedly merges the most frequent pairs. The word understanding might become 3 tokens, understanding. The word the is so common it stays as 1 token. A rare word like numen-ultramicroscopic silicovolcanoconiosis gets split into many small pieces. GPT-4's vocabulary has about 100,000 tokens. On average, 1 token is about 4 characters or 3/4 of a word. When you hear that GPT-4 has a 128K context window, that means 128,000 tokens, roughly 96,000 words or a 300-page book. Let's trace exactly what happens when GPT processes the prompt, "The cat sat on the." Step 1. Tokenize. This becomes 5 tokens, each mapped to an integer ID from the vocabulary. Step 2. Embed. Each token ID is converted to a 768-dimensional vector using the embedding matrix from episode 8. Step 3. Add positional encodings. Each position gets a unique signal so the model knows word order. Step 4. Pass through n-transformer blocks. Each block applies multi-head attention from episode 7, then a feed-forward network with GLUE from episode 6. Residual connections and layer normalization keep gradients flowing. Step 5. The final hidden state of the last token passes through a linear layer, producing 100,000 logi, 1 per token in the vocabulary. Step 6. Softmax from episode 9 converts logits to probabilities. The highest probability token might be MAT at 35%. The model has a probability distribution over 100,000 tokens. How does it pick one? The simplest method, greedy decoding, always pick the highest probability token. But this is boring and repetitive. Instead, most models use sampling with temperature. Remember temperature from episode 9? Low temperature makes the distribution sharper. The model is more confident. High temperature makes it flatter, more creative and random. Top K sampling. Only consider the top K most probable tokens. Ignore the rest. Top P sampling, also called nucleus sampling. Only consider tokens whose cumulative probability exceeds PE, say 0.9. These techniques balance coherence and creativity. That temperature slider in ChatGPT, now you know exactly what it does mathematically. Now we generate a full response. The model predicts 1 token, appends it to the input, and runs the whole thing again. The cat sat on the mat. Now the input is, the cat sat on the mat. Run again. Period. The cat sat on the mat. Period. Run again. Next sentence starts. Each token is generated by processing the entire sequence through all transformer layers. For a response of 500 tokens, that's 500 forward passes. Each forward pass processes a longer and longer sequence. This is why longer responses take more time and more compute. This is also why there's a maximum context length. The model literally can't process more tokens than its positional encoding allows. Everything we've described is inference, generating text, but how is the model trained? The objective is remarkably simple. Predict the next token. Take a huge corpus of text, trillions of tokens from books, websites, code, conversations. For each position in the text, the model tries to predict what comes next. It sees the cat sat on the and should predict mat. It sees to be or not to and should predict be. The loss is the cross entropy from episode 5 between the predicted distribution and the true next token. Backpropagation from episode 4 computes the gradients. Gradient descent from episode 2 updates the weights. Repeat this billions of times across trillions of tokens, and the model learns grammar, facts, reasoning, coding, all from predicting the next token. Let's zoom all the way out. What have we learned in this series? Episode 1, the model makes predictions using parameters, weights, and biases. Episode 2, It learns by minimizing a loss function through gradient descent. Episode 3. Neural networks use nonlinear activations to model complex patterns. Episode 4. Backpropagation efficiently computes gradients through the chain rule. Episode 5. The loss function defines what good means. Episode 6. Activation functions like ReLU and GeLU enable deep learning. Episode 7. The transformer uses attention to process sequences in parallel. Episode 8. Embeddings convert discrete objects into meaningful vectors. Episode 9. Softmax produces probabilities, cross-entropy measures quality. Episode 10. Tokenization, autoregressive generation, and next token prediction tie it all together. That's it. That's the math behind AI. If you've watched all 10 episodes, you now understand the mathematical foundations of modern AI better than 99% of people who use it every day. Not the hype, not the analogies, the actual math, linear algebra, calculus, probability, applied at massive scale. Whether AI continues to advance or hits fundamental limits, these mathematical principles won't change. They are the bedrock. Thank you for watching this series. If it helped you, share it with someone curious about how AI really works. And if there's a topic you want me to cover next, maybe generative adversarial networks, diffusion models, or reinforcement learning, let me know in the comments. I'm a math teacher. My job is to make math make sense. See you in the next series.